So in this chapter, we're going to introduce radical reactions. Radical reactions involve radicals that have a single electron. In all the previous reactions we've had are ionic reactions, where we made ions, but now we're going to be making radicals. So let's look at the two types of reactions. In ionic reactions, the ones you're used to, we have heterolytic bond cleavage. We move two electrons, and when we show this on diagrams, we do a two-headed arrow, double barbed. Radical reactions have homolytic cleavage. Only one electron is moved, and to show that there's only one electron, we have a fishhook arrow. In a heterolytic bond cleavage, this is the ionic, what we would have is these two electrons here would both be transferred to the Y, and we would make an X that has a positive charge because it's minus 2 electrons, and a Y that has an extra set of electrons on it and would be negative. But with homolytic bond cleavage, one electron goes to the X and one electron goes to the Y, and we make two free radicals, X and Y, and they each have a single electron, making them radicals. We need to look at the structure and geometry of these radicals because when they react, that will influence the structure that we get. A carbocation has a trigonal planar shape. With 0 non-bonding electrons, it's sp2 hybridized, and so it's flat. A carbocation, though, is trigonal pyramidal. It has 2 non-bonding electrons and is sp3 hybridized and has this structure here with 2 bonds in the plane, one in front and one behind. Okay, the carbon radical is going to be mostly trigonal planar. It has 1 non-bonding electron. This is going to be important because once we make a radical, it can be attacked from either the top or the bottom evenly most of the time, and so we need to know the structures that'll be formed from those attacks. So the stability of these free radicals is going to be very similar to the carbocation stability. The methyl is the least stable, primary, secondary, and tertiary increasing in stability. And the reason for this is the alkyl groups stabilize the unpaired electrons via a delocalization effect. And the order of stability that we just gave you is supported by bond dissociation energies. So if the radical is more stable, it takes less energy to break the bond. And so to break this bond takes 381, but to break this bond down here takes 435. So what they're saying is that the radical that's formed is more stable if it's got these alkyl groups around it. We want to rank the following in order of stability. So first let's look at them, and that this one is primary, this one is tertiary, and this one is secondary. So we would expect the least stable to be this one, least. Right, least there, and we would expect the tertiary to be the most stable. Again, this one is secondary, this one is tertiary, and this one is primary. So we would expect the tertiary to be the most stable and the primary to be the least stable, and the secondary to be in between. Resonance structures are also important to the stability of radicals. And what we're going to see is we're going to see an unpaired electron, and it's going to be allylic to the pi bond. That means it's one away. And when it is one away, we're able to get these resonance structures. And that's very stabilizing. A free radical in a benzylic position, which would be here, is also very stabilizing because you can make all these resonance structures. So if you're ordering the stability, resonance stables the radicals even more than being tertiary. So if you have choice and you're trying to figure out which one's more stable, the ones with resonance are more stable, and then the tertiary, and then the secondary, and then the primary are not very stable at all. So let's draw the resonance structures for these radicals. Okay, so let's start with A. We're drawing resonance structures now, so we're not changing any bonds or the structure. We're just moving the electrons around. And what will happen is this electron here, will go and make part of a pi bond there. One of these electrons will join that electron in making the pi bond. The other one will make a free radical here. So what we'll end up with is, go back to this, there'll be a double bond here, and the radical has been moved. Okay, so let's look at the next one. Here we have a radical. It's going to be part of the pi bond here, and one of these is going to join it in making a pi bond, and the other one is going to sit on that carbon right there. Oops, I made a double. It should be a fish hook. I'm used to making double-headed arrows. Okay, so that will give us, let's get my color right. We didn't do anything to this bond, so it's still sitting there. There'll be a double bond here, and there'll be a single electron sitting here. Now we have the same thing again. This electron that I just drew is allylic to the double bond in the far right. So it'll happen again. We'll get, this will go here, and one of these will go here, and the other one will go here. And this may not be a very stable structure because we're making a primary, but we'll go ahead and draw it. There we go. We've got a bond here, and we've got the new bond we created there, and we've made a radical there. So let's look at this last one. We have a radical down here. It's going to combine. It's going to go here, and one of these will go here and join it, and the other will make a radical here on the top. So that gives us a new double bond. Oops, I didn't change my color. A new double bond here, a free electron here, and the bond that we didn't do anything with there. Now we've got this new radical is allylic to the other double bond, so it will go here. One of these electrons will join it, and the other will make a radical. So we have the bond that we didn't do anything to. We've got the new bond that we just created, and we've got a Okay? So you move them around just like you moved around double pairs of electrons before. One of the important skills in this is going to be identifying the weakest bond. And I just got rid of the answer. I want you to see that. Don't look. So we're looking for the weakest bond. We're going to want to consider all the possible radicals that could be created by homolytic cleavage. So everywhere that there's a hydrogen, we could take that hydrogen off and make a radical. So if we take the hydrogen off here, we'll make a primary. And we know that that's not going to be very stable. And it's the same thing here. This one would also be primary. Here, we'd get a tertiary, so that's pretty good. Let's mark that one. That one would be a tertiary. I like that one. Beware of the orange one here. There are no hydrogens to be pulled off, so it's not possible to make a radical there. Okay, so then the bright pink one here is going to be a secondary. And then we have these that are on the double bond. Those are not going to be very reactive. That's not stable. So you might think that the tertiary is your best bet, but it isn't, because this pink one here is stabilized by resonance. We can draw another structure here where we get the double bond here and the radical is there. And this is a resonance structure, and so the pink position is the best one. So let's identify the weakest carbon-hydrogen bond in each of the following compounds. Remember that the weakest carbon-hydrogen bond is going to be the position that's going to make the most stable radical. So if we pull a hydrogen off of this position, we'll make a primary radical, and that's not very stable. And the same goes for this position and this position. Those will give you radicals. We look at the orange position here. There are no hydrogens to be pulled off there, so we can't make a radical at that position. We can't add an extra electron either. Okay, so let's then look at these two. The green ones here will give us secondary radicals, and that's better than the primary ones that we looked at before, but not quite there yet. There are hydrogens at, we'll put them here, there are hydrogens here and here, but those are not going to be stable. They're not going to make stable radicals. So that leaves us with our last hydrogen. We have a hydrogen that's coming, we'll do here in green. We have a hydrogen that's coming off there. If we pull that hydrogen and put a single electron there, we'll have a tertiary, which is great, better than the secondary that we had before. And it's also allylic to this double bond, and so that it will be the weakest carbon-hydrogen bond. This will be the hydrogen that gets removed. If we look down at the next one, if we pull a hydrogen from here, this will be primary. That's not going to be stable. If we pull a hydrogen from here, okay, the green position will be secondary and allylic to the double bond. So those are both really good things. But what if we pull this electron? If we pull not that hydrogen, if we pull that one, it's tertiary and allylic. And so that's going to make the most stable free radical, if we can put a free radical there. And let's look at this one. First, we'll mark all the primaries. None of those are going to be any good. We don't want to use the primaries usually. Okay, so those are going to make primaries. Those aren't going to be very good. There is no hydrogen here, so that's not going to be very good. We've got these guys that are involved in the double bond. They're no good. So the last one we have left is, we're going to do blue, is one that's here. And this actually is going to be our most stable option. It is primary, but it's allylic to that double bond. It will be stabilized by resonance. And so that is the blue one here is our best option.